In last week's videos, we reviewed the Laplace domain and Laplace transforms that we can use to convert time domain functions into the Laplace domain. This week, we're going to introduce the concept of a transfer function, which is a Laplace domain relationship between an input variable for a model and an output variable for a model. The transfer functions describe relationships between quantities in the Laplace domain, and these help to simplify otherwise more complex relationships that would be represented by ordinary differential equations in the time domain. We'll introduce these using some simple examples of models of chemical and biological processes, and we'll talk about integrator, first order, and second order transfer functions. Let's start with a storage tank. So suppose we write a simple time domain dynamic mass balance for the quantity of fluid in a storage tank. The rate of accumulation of mass in the tank is equal to the difference between the rate at which material enters the tank and the rate at which material leaves the tank. If we assume that the fluid has constant density, then the rho can be factored out of this equation, and we can write a dynamic model equation for the change in the height of the fluid in the tank, where A represents the tank cross-sectional area. Now let's consider what happens if the tank is operating at steady state. If it's operating at steady state, then of course none of the important process variables are changing with time, and the time derivative of the height must be zero. That is, there's no accumulation. We'll indicate that the flow rates are at their steady state values with the bar accent on top of the variables. Next, we'll subtract the steady state equation from the dynamic ordinary differential equation. This enables us to write the model equation in terms of what we call deviation variables or perturbation variables. Deviation variable and perturbation variable are synonyms. Throughout our text, the deviation variable is indicated with a prime, and it represents the dynamic variable minus its steady state value. So qi prime is qi minus qi bar. Q prime is q minus q bar. And for the height, h prime is h minus h bar. Now we can substitute these deviation variables into the ODE. When doing this, we note that the time derivative of dh dt is the same as the time derivative of dh prime dt, because if we take the time derivative of this definition of the deviation variable, the derivative of dh bar dt is 0, since it is a constant. Next, we take this into the Laplace domain. Now, one of the advantages of writing the dynamic model equation in terms of the deviation variables is that often we'll be describing situations in which the initial values of all of the variables are their steady state values. You'll remember from the last chapter that the Laplace transform of the time derivative of h should be s times h minus the initial value of h. And since we've written this in terms of the deviation variable, the initial value is 0, so that term goes away. Of course, the Laplace transform of qi prime is capital Qi of s, and the Laplace transform of q prime is capital Q prime of s. Now we can solve this algebraic expression for the output h. Our two model inputs are qi prime and q prime, and the Laplace domain functions of s that multiply the inputs to determine their effects on the output are what we call transfer functions. Now, if only qi prime is non-zero, then we can say that h prime over qi prime is 1 over as. Similarly, if only q prime is non-zero, then h prime over q prime is minus 1 over as. We'll call these the transfer functions g1 of s and g2 of s. g1 of s tells how changes in input variable 1 affect the output variable, and g2 of s tells us how changes in input variable 2 affect the output variable. Remember that because the Laplace transform is a linear operator, it obeys the principle of superposition. That is, the effects of these two input variables, qi prime and q prime, can be added together to give their total effect on h prime. So if both qi prime and q prime are changing, their effects can be added together to obtain the effect on h. Alternatively, we could define a difference between these two variables, q delta prime, the difference between the inlet and outlet flow rate in the Laplace domain, and write a single transfer function relating them. This works in this case because the transfer functions g1 and g2 have the same form, 1 over as. It's just that one of them has a minus sign. In this case, g1 of s, g2 of s, and what we call g of s here all have functionality s to the minus 1, where s is the Laplace domain independent variable. These are a special type of transfer function that we call an integrator because of their time domain counterparts. In the time domain, if we wanted to solve for h as a function of qi and q, we would integrate this equation. Remember that integrating with respect to time in the time domain is the same as multiplying by 1 over s in the Laplace domain. For an integrator transfer function, the output will always be proportional to the integral of the input in the time domain. In the next video, we'll look at an example that gives rise to a different kind of transfer function called a first-order transfer function.